All right, so this is chapter 20, lecture on transition elements and coordination chemistry. So key points for this chapter for test 5, electron configurations. This is kind of more of a review from 151 material. Properties of transition metals, oxidation states, and chemistry of selected one. Again, this is a little more flavor material. When down here is really where we're going to get into the meat of it about coordination compounds, ligands, naming compounds, a little bit on that, bonding in complexes, crystal field, and talking about isomers, enantiomers, molecular candidates. This is going to come up in the organic chapter in a little more detail as well. A little sidebar about the color of transition metal complexes, and then looking at how nitrogen is acquired by living things and different kinds of organometallic enzymes and stuff like that. So areas not to focus on, don't memorize any of these standard potentials or anything we're going to run into, or drawing any of these compounds. We're not going to really focus on that. You may need to identify something or name something, but I'm not going to focus on the drawing of this per se. There'll be enough of that in the organic chapter that's going to follow up from this one. So when we talk about transition metals, right, we're talking about metals in the D block, so they're in the middle of the periodic table, the transition between the S and P blocks. So these will be metals like iron and copper and zinc and chromium. In which a central metal atom or ion, usually compound. Similar is true for coordination compounds. Ligands are the molecules or ions that surround the central metal atom in a coordination compound or complex. Ligands are coordinated is how they describe it, and that bonding is best described as covalent in nature. It's like a covalent metallic interaction. It's not really ionic in nature unless there's some kind of ionic thing going on where something's ionically bound, but then typically we would think of this as like an ionic compound. So there are some compounds that are kind of in between being ionic and have semi-ionicness to them, and then also have coordinated ligands too. So like I say, this is sort of a bridge which kind of brings in all different kinds of bonding, right? You've got these molecules that are covalent in nature, pushing electrons into a metal that interacts with them with some metallic nature and creating these kind of covalent coordinate bonds. Then you may also have ions that are ionically bonded to the same metal atom in the center, and they may also interact. But typically ligands, they're distinguished from an ionic compound because we don't have like a true lattice. Remember that, like, to be an ionic compound, you've got to have a true lattice. But within the coordination compound, what forms is these things that surround this center and not like a true lattice structure. So these are other ways you can look to distinguish, right? And the coordination bond in the coordination compound has this covalent character to it. So that's another thing we want to look for to distinguish from an ionic compound. And also we've got this metal in a center thing going on, which is different from typical molecules that have nonmetals associated with each other. So these are all things we want to look for that distinguish this new sort of class of compound. It's not really new. We've seen them before, especially in like hydrates, examples of hydrates, where you have some metal and water complexes with it, and that forms this little coordination group, and that's the coordination compound. So we'll see how some things we've seen before actually fit into this category, but we never really talked about it in detail. I like to talk about it here because it's going to be a good segue into organic presentations and into things like stereochemistry and the structure of kind of more complex things, but we can break them down into little pieces. So it'll help us out with that. Coordination number, the number of ligand donors around the central atom. You can also have chelates. These are rings formed around the atom by polydentate ligands. So these are ligands that can coordinate with multiple of their donor atoms. Typically what happens is ligands push electrons into a metal because the metal is either positively charged or it has empty d orbitals, so it's usually electron accepting, and so ligands push electrons in, and that's how they get attached. But that they don't push them in totally. So that's like a sharing. So it's like a coordination. It's like a covalent type of interaction. Again, we'll see more about them. Ligands can be monodentate. They can bond once, twice, or multiple times. They can form little rings around their central atom. We'll see that. That's this chelate ring. And just for more specificity, a chelate is a complex that has 2 or more of these rings. So you're like trying to surround the metal. This can be important for like treating certain kinds of metal poisonings. You introduce some kind of ligand that will chelate, that will surround this metal ion so it can't do more damage, and then it can just be removed from the body. This is an example of something where this chelation comes in and what that refers to. We'll also see isomers. These are compounds that have the same formula but different arrangements of constituent atoms and a variety of different kinds of isomers. I like the presentation of isomers in this chapter actually more over how it's presented in the next unit on organic, because it really does break down all the different types and go into a lot more of a presentation of the idea, right? So a constitutional isomer, these have different connections. So these are just put together differently. They have the same formula, but these are just entirely different compounds. Like one may have something completely different in the center, some completely different structure entirely. Linkage isomers arise with a coordinate compound, like the kind we've looked at, these metal complexes, where a ligand can bond through one of its donors or a different donor. These change the properties, right? These constitutional isomers, these totally different properties. Same with these linkage isomers, totally different properties. Ionization isomers, so these could differ whether the anion is coordinately bonded or whether it's associated as a counterion. Again, these are totally different. When we get into stereoisomers, now we actually get to different isomerizations where the isomers may have similar properties to each other. They're distinct, still very distinct chemically, but at least more so similar, right? So in stereoisomers, they have the same connection, but a different arrangement in space. Okay, so they're differently arranged in space, but the same things are in the center, the same things are connected to the same things, but their relative orientation changes, right? Diastereomers are the first type. These are non-mirror image ones. These are chemically very distinct. Okay, similar to the above, but a little more similar. Like cis and trans isomerization, where the ligands are on the same side with each other, with the same ligands, or they're on opposite sides from each other. These are just ways of classifying them. But these typically can have radically different melting points, boiling points, very, very, very different properties. So we'll also run into the mirror image versions of these, which will have similar properties, and we'll talk about those a little bit as well. Those are called enantiomers. These are compounds that are mirror images that are not identical. They're like different left and right hand versions of molecules or complexes or other structures. These tend to have similar chemical properties, almost identical, except when they interact with things that are also chiral, other-handed things, right? Examples of this would be in like amino acids that form polymer chains. Generally, they all want to have the same handedness to form the most stable configuration. And if they stick in one that has the opposite handedness, that can actually disrupt the structure. We'll see more in detail about how this works. But enantiomers, chiral things, their chiralness generally does not become as significant to their properties unless they interact with another chiral thing. That's a thing to keep in mind. These enantiomers, these mirror image molecules, essentially act identically and have like identical boiling points and freezing points and such, unless they interact with something else that is chiral. That tends to be a requirement. Achiral are things that don't have this three-dimensional handedness property of enantiomers. And again, we'll see more about this in a bit. We'll see mixtures, a mixture of the one-to-one mixture of enantiomers. And we'll also see things that are paramagnetic substances that have unpaired electrons that are attracted to a magnetic field, albeit more weakly than ferromagnetic materials, which make up traditional magnets. Ferromagnetic materials make up traditional magnets. Or diamagnetic, things that have paired electrons and they're repelled by a magnetic field, again, more weakly than ferromagnetic materials. We'll see this again a little bit as we study the electrical structure of metals and complexes here. Again, we'll talk about high spin complexes. These again describe the transition metal complexes or just metal complexes generally. Typically, when we talk about spin and crystal field and such, this is very specific to transition metals because it has to do with the d orbitals. Sometimes other metals that have active f orbitals can also be pulled into this kind of discussion. This is related to crystal field, which has to do with looking at how the d orbitals split. They become non-degenerate so that there can be a group of things associated with one energy of d orbitals and another group of things associated with another energy. This tends to result in these complexes having bright colors and tends to be an explanation for their bright colors because of the gap between d orbitals and the way they can be electrically excited to send electrons up or have electrons fall down through this gap. And the gaps between these d orbitals in a crystal field structure in a metal complex that has crystal field splitting typically matches up with like visible light or near visible light. So that tends to be an explanation. So when you have the high spin complexes, they pair up to give the maximum number of unpaired. This is your traditional Hund's rule, but sometimes depending on the structure, that's not possible, and so they may actually attain a lower spin. And when we talk a little more about crystal field theory, right, that's that energy gap between the two sets of d orbitals that occurs upon association with the ligands. It's kind of like when a molecule forms, if you remember about like molecular orbital theory, like these new molecular orbitals form from the atomic orbitals. In crystal field, the crystal field splitting occurs when the metal ion or atom associates with its ligands. So the ligands affect how the split happens, but other parameters can affect this too, like the temperature and parameters of structure and which metals you pick, everything else. But typically the ligands pull on the metal, and they're associated with different causes of gap between the d orbitals when the split occurs. And that's where we get weak field ligands, ones that don't split the crystal field as much, and those that are strong ligands, and they cause more crystal field splitting, increase that energy gap so that a higher energy photon could excite between them. And we'll see a little more about that. So this is just a reminder of what we're talking about when we're talking about transition metals, right? So we're looking here at the center of the periodic table, the D block. We might also be looking at F block. Sometimes they consider these to also be inner transition or something like that. But F and D are generally the things we are discussing in this chapter, though focusing predominantly on D. There are very particular properties associated with D electrons that are not quite the case with F electrons in all cases, but in some cases, yes, like both groups of these can form these kinds of coordination complexes. It's also possible even to take some P metals and form these kinds of complexes, less commonly with the S metals, but some P metals can also do some complexing. But we're going to focus here conventionally and predominantly on the transition metal group in the center. So when we look at the electronic structure of these transition metals, right, we remind ourselves that they have d electrons going on here. But if we look at the S block ones, they don't have any d electrons. So like I say, they're not generally associated with this process, right? And then when we begin filling the d subshell with scandium, then we see that we get our first d metals. The filling of the d subshell generally proceeds according to Hund's rule, right? So things will fill and then they'll go back and pair. We've got exceptions with chromium and copper. Again, this is mostly review to help us remember that when you have half-filled and fully filled shells, D will try to fill itself by pulling from the previous S, because this S actually fills before this D, if we remember the order of filling. Again, not going into too much detail about this. It's evidently advantageous to shift one electron from 4s to 3d, which decreases the electron-electron repulsion and gives two half-filled subshells. That's generally more stable. This is one of the first kind of D properties that we've talked about previously, that you've seen in a 151 class, and it's important to keep in mind how D metal and D orbital chemistry controls what goes on with these metals and how their complexes form. And again here, similar things can happen when a metal loses electrons to form a metal ion, a cation, a positively charged ion. So similarly, when we lose electrons, we typically will lose electrons in such a way as to give half-filled and fully filled shells, so that things can lose electrons typically from this S space first before D, and that's what they're discussing here. Again, this is something you should remember from 151, but we're just talking about it again here so that we can see how D has its own sort of traditional rules of filling and unfilling. And they look here at some of the conventional properties. Again, you don't have to memorize this, but we can see trends going on here. As we fill D, we see things go on here with the conductivity. There's some parameters. It goes up, and then it goes down, and then it goes up again, then it goes down. We look at melting points, right, where we see where melting points kind of peak, where you get the highest point is somewhere kind of in the middle, closer to the middle of the table. We're seeing like our highest stuff. as the D field fills up, and as it builds up, the D metal properties tend to be the strongest sort of in the middle of the D electron space, where the chemistry of the metal is predominantly controlled by the D electrons. And then they talk a little bit about labeling, like how some tables will label the center of the table with like a 1A to 8A because their valence configurations are similar to those of analogous elements. I've found this to not be entirely the most useful, but the way that they're doing this is they're adding up the electrons, you know, between D and S, but D electrons have different chemical properties from S electrons, so it's not always the most useful when we think about like how complexing goes on and works, because these electrons have different levels of accessibility and different types of properties in terms of what they can do. So it's just something to keep in mind. So thinking about metallic properties, right? These transition metals are typically like, you know, your metal's metal, right? They typically have high melting points. They typically have a silver luster. They typically are malleable, lustrous, and they have high electrical conductivity because of the smearing that occurs in the d orbitals. The d orbitals kind of like act sort of like as a continuous field, and that allows for easy excitation and de-excitation within the d orbital space, and that makes them highly conductive generally as materials, which is not typically true of molecular compounds or just atomic things like argon or something like that, like a gas. So that's just something we generally see. We also generally see high melting points because the metal field, the D field, holds everything together. And we'll talk a little bit more about how that's related to crystal field and stuff later on. We're not really going to focus too much on bonding. We're just going to talk about how, you know, the melting points increase as the number of unpaired D electrons available for bonding increase and then decrease as they fill up. So we typically see this kind of peaking and curving with a little bit of exception kind of here in the middle, but we generally see a trend in this sort of direction where we get a peak and then things kind of go back down in terms of the metallic properties, which tends to be about in the middle of each D series of metals on each row, where you have the maximum number of unpaired electrons. The D orbital space has the most flexibility, conductivity, and governs the properties of the metal the most when it's got the most unpaired D electrons. So they also talk a little bit here about shielding and about lanthanide contraction when we talk about the F block and some other properties where, you know, it depends on how the electrons are associated and where their energies are and how effective nuclear charge increases. D electrons don't really shield as much. They fit into more of a space, and they don't generally increase the size of the atom as much as adding other types of electrons because of how much space there is for electrons to fit in with regard to D. So these are just other points to kind of keep in mind. We'd expect to see an increase in size, but there's some other quantum effects that go on that cause these contractions. We don't need to delve into it in as much detail, but just understand that the upturn in radii at the end of each series is probably due to more effective shielding as double occupation of the d orbitals is completed. So as we get more and more electrons, they get more compact, then we start to see a faster increase in the radius. And they show that the radius decreases and then increases a little bit here at the end. As we open up D, it increases and then decreases. Remember that generally speaking, we expect to see the radius decrease as we go along the periodic table. That's just the general trend that we expect to see because the protons pull more strongly than each additional electron adds. So a general decrease is expected, but these little bits of uptake have to do with the closure of the D space here at the end, and thus the addition of electrons actually increases the repulsion, and that's what they're talking about here. They talk about lanthanide contraction. Lanthanides can actually decrease. This is kind of in the F block due to larger Z effective compensating for the expected size increase due to added shells of electrons. So we actually see a decrease close to the end of those for the closure going on in that space. But in any case, this is more just kind of note for trends because we're not going to get in too deep to the F elements, but just be aware that there are some additional interesting trends that go on that sort of defy the trends that we've We focused on and learned from like a 151 perspective due to the fact that there are more complications with half-filled and fully filled shells and additional electron repulsion. That's kind of the key takeaway here. As the density increases and then it decreases. If we look at things like ionization energies, right, so we're going to be removing electrons from metals. These typically metals lose electrons. That's a typical expectation, right? So what's going on here? Except for copper, all the E cell reductions here are positive. So E for oxidations are positive. Sorry, that's the way I meant it. So they talk about here it being oxidized because typically they write the cells as reductions. So all of these are generally positive except for copper. Copper actually can be said to get a little less stable when you remove electrons from it. There's a whole thing for that, but it has to do with that pulling that 10th electron in and going from that half-filled S and half-filled and fully filled D to a now unfilled S position as we remove electrons. So here what we're talking about is the removal of electrons, right, and typically is positive. So if you coupled it with hydrogen, it would be spontaneous. Most metals are easily oxidized. Most metals are oxidized rather than reduced when compared to the hydrogen standard electrode. That's really what we're getting here. And thus, since they're positive with respect to the hydrogen electrode, they can also be oxidized by typical acids. And the family of copper is the one that tends to be more resistant to that, like copper, silver, and gold. So they give us this example of conventional first row here of D metals. As you go down, you get like silver and gold, and they also have some resistance to oxidation. But this gives us an idea of the trend that typically right here on the end where we have the most stability due to the half-filled shells, that tends to also be the hardest to oxidize. So these early transition metals also tend to be oxidized most easily as well because we don't have an accumulation of D electrons to remove, and by removing it we can completely empty out the D, and so that tends to be more stable. That's why we tend to see states like for things like scandium and vanadium of just emptying out the electrons entirely, S and D entirely. And as long as that doesn't result in too high of a charge, that tends to be the most common oxidation states for those metals. And this differs from other metals, right, because they have a single oxidation state. But the reason that transition metals tend to have multiple oxidation states tends to be the way they can reach stable configurations of their D space by losing electrons. So for example, you can have different oxidation states for like manganese, because in these different configurations, there's some stability to be had within the D electrons, and we're just losing electrons out of D and S to reach these states. And we also see that as we do so, we're seeing some interesting properties happening here. At these higher and higher oxidation states, they talk about how we transition elements frequently have oxidation states less than their group numbers, but permanganate tends to have a lot. Manganese tends to have a lot of oxidation states. And that's common once you start having enough D electrons to support those states. Again, they talk about vanadium and chromium can form a variety of different states, but it's all about where they can find half-filled, fully filled, or other ways of arranging their configurations of electrons to try to achieve some stability, but they do have those electrons to lose. And so those higher oxidation numbers do exist because they have those electrons to lose from S or from D. They look here at the different numbers of states, right? Manganese has a lot of states. Chromium has a lot of states, and they put the ones in red that are common, I think is what they tried to say here. Typically, like here for titanium, the +4, right? It lets me empty out everything. It empties out the 2 Ds and the 2 Ss. Scandium here empties out the D and the 2 Ss. Vanadium can do that, but now when we start to reach these higher states, it becomes more difficult unless they're in an ionic grouping, unless they're in some kind of grouping that can help support those higher states. Again, we typically do not see free ions with charge states higher than 4. That's just not very common. Typically not even higher than 3. It's just hard for a single ion to support that much charge. But as we move across, there becomes less flexibility as the d space gets filled. So we have fewer and fewer possible states that are stable, and so we'll maximize somewhere in the middle of the d space and then go back down. That's the point that I'm trying to bring home here. So for group 8b transition metals, though, the loss or sharing of all the valence electrons is electronically prohibitive due to the increasing value of Z effective. So it's harder to remove the electrons. So, for example, the +6 and +3, only lower oxidation states are available for those metals. These species have a great tendency to be reduced to still lower states. The aqueous CO3+ ion is unstable, and therefore it forms CO2+. It's unstable in the presence of water, but it does form. In general, ions that have the transition metal in a high oxidation state tend to be good oxidizing agents. That's generally true. Conversely, early transition metals, ions with the metal in low oxidation states are good reducing agents. Again, this is generally true. Divalent ions of later transition metals in D block are poor reducing agents because of the large value of Z effective. In fact, zinc has only one stable oxidation state. You should remember this from previous discussions. Again, we're going into a little more detail with this, but I'm assuming you come in with the basic knowledge that we've seen in 151, and now we're just sort of discussing why that is in a little more detail. So here we look at chromium and some of the specific chemistry of chromium, use of it in making steels, looking at it. Pure chromium is made by reducing chromium oxide with aluminum. Aluminum, of course, gives electrons away pretty easily. It's kind of like magnesium and sodium and some of those other metals that are pretty readily oxidized, right, to free up other metals from their the salts that they're found in, the ionic compounds that they're found in, and that's also what we see going on here as well. Chromium is hard and lustrous and takes a high polish and resists corrosion due to an invisible microscopic film of chromium-3 oxide. So it's one of those metals that can shield itself. It's used to make thin plates on things, chrome bumpers and things like that, whether or not that's really used to make all of them anymore. It's also used to help make steel less susceptible to corrosion. And they talk about in acidic solutions versus basic solutions, the directions you can draw these in, because chromium has these three common oxidation states that we've seen before, like we've seen dichromate, you probably run into that, or chromium-3 in various problems. These are all common states for the chromium ion, ion to be in, and they're all stable because of the availability of all those d electrons. So these are stable positions, and they can form different compounds with generally pretty bright colors as well. And we'll talk a little bit about how that happens, because some of these ions, these various ions, some of the ones in here, can be thought of as having complex-like properties as well, and may experience some crystal field, which may be resulting in some of these compound colors. So when Cr is bound to 6 water molecules, they talk about this here. And when it replaces some of those anions, replace some of these, we can think about this as a complex, right? We can think about the fact that some of these, like the chlorines, may be better described as being ionically bound, but because of the presence of the water, we end up with these structures instead of a true lattice. And that's where this can become a complex instead of just an ionic compound, right? When we bind up with waters, we can get these kinds of complex appearances, and this becomes like a unit of it instead of it just being like a free ion. And that gives us an idea of how many things can coordinate to it, and we'll see that as we move on. But these green complex ions are the result of these replacement of water with chlorine ions. So these are ions, so it's like an ionic compound, but it's also got these waters. And the waters are not ionically bound. The waters are covalently coordinated. So the complex has both ionic and covalent components to it. And we'll see that shows up sometimes, frequently sometimes, depending on the behavior of the metal, right? Is the metal's bond with these counter ions more covalent-like, in which case it doesn't form a true lattice like an ionic compound, or is it more ionic-like, in which case there is a testable true lattice? That boundary is sort of where some of these metals end up. They're sort of in the boundary between being ionic and covalent with the metals. It's kind of like when we talked about polar covalent molecules. These have kind of a similar thing going on. So, and it would depend on the relative polarity and the relative strength of the pull, whether or not they end up more so, and how well they fit and how tightly and how much the lattice gets constructed, as to how much we can think about these as coordinated versus true ionic compounds. In a 6+ state, They say the most common solution species are yellow chromate ions and orange dichromate ions. These are interconverted with a rapid equilibration reaction, so both of these are present. These can also be basic, amphoteric, or acidic, depending on how many waters they have associated with them, forming these hydroxides, how many hydroxides they have here with them. They also talk here about other metals like iron, right? Iron is typically a very characteristic D metal, right? So it can react in the presence of acids, where iron reacts in the absence of air with an acid like HCl, which lacks an oxidase. It is the green iron 2 ion forms. The oxidation stops because the reduction potential here is negative, but it can also be slowly oxidized by atmospheric oxygen to iron 3, and that's the traditional rust iron. The orange rust iron that we typically see is the result of this iron 3 forming an oxide. When iron 3 is treated with an acid that has an oxidizing anion, dilute nitric acid, the metal is oxidized directly to iron 3. Iron likes to have this additional oxidizing power. Acids like HCl typically are not enough for quick reaction, but they do react with it. They can be dissolved by acids. The addition of a base results in a gelatinous red-brown hydrous oxide, this metal 3, iron 3 oxide, and there can be a hydroxide form of it too, but this is where that red brownishness that we've been talking about, characteristic of rust, starts to come in as well. Copper is a lot less reactive than other transition metals, especially the early transition metals, like the ones in that first row of the D block. It's generally resistant to corrosion, but further exposure, prolonged exposure to O2, CO2, and water and moist air, especially in the presence of salts that can help to facilitate electric exchange, can result in the green patina. It's like the Statue of Liberty, right? We remember the Statue of Liberty used to be copper colored, but over the course of decades it turned green from the reactions with the air and the salty water in the bay. Over time they react, and this is a protective coating for copper, so the internal structure does not further corrode. Like aluminum, magnesium, and other metals like that, the green patina is protective of the copper substructure. So it's not like iron where it corrodes entirely. It's more like the other metals that get coated. So they get coated in this green patina seen on bronze and monuments and copper statues when they're exposed to air, especially salts, for long periods of time. I talk about the further reactions that can be done with this, whether into the copper 1 or copper 2 states in the 2 steps that takes. Dilute nitric acid can oxidize copper, typically acids that do not possess a further oxidizing step, which includes those acids like HCl, HBr, HF, those HI. Those don't possess a further strong enough oxidizing step typically. Nitric acid is extremely oxidizing as well as being an acid. The presence of the nitrate helps to couple with this process and allows for the loss of the gas, various nitrogen oxides, in this case the nitrogen monoxide gas, nitric oxide, sometimes it's also called gas, that leaves, and that helps to drive this to completion, and we get a positive voltage. So in the presence of some acids, you can get a reaction. So it's still not necessarily any strong acid. You've got to have a strong acid with an oxidizing component. This will be a topic for later on when in an organic class they'll go into the details and separations between different kinds of acids and how you can use them. But this helps to explain why, at least from a metal context, some acids work where others don't. And we see the disproportionation reaction. This is typical where copper 1+ would rather be copper metal or copper 2+ due to the greater stability of the copper 2+ and neutral copper versus copper 1. All right, so this is the end of the first presentation on Chapter 20. We'll continue along with this in the next one. Thank you so much, and I'll see you all again.